In this next section, we're going to be using our understanding of logarithms and their properties with exponents, all their properties for that matter, to help us solve equations. It's actually kind of fun. I think it's a little bit more challenging than some of the other sections, but challenging, I don't find it particularly hard, just requires a little bit more ingenuity. So let's take a look at what I'm trying to say. What would I do? So in the classroom, I would give you this illustration. If I gave you this equation here, and I said, hey, what's the value of x? You instantly would know that the value is 2. And what you may not even realize is that you didn't even care that this was a fraction with all of the denominators being over 6. It was irrelevant. All you really needed to do was 2 plus 1 equals to 3. Well, we can have a similar situation if we have exponents that are to the same base. They're both to the base of 2. Well, we could prove this with some logarithms, and we could do some fancy work to show that this is the case and everything's going to drop out. But the reality is it's the same as this. The 6's in the denominator had nothing to do with it because they were all the same. Well, it's here, same here. The 2's have nothing to do with it, and all we need to solve is the exponents. The x minus 1 can just be set equal to the 2x minus 4. Now, we solve that in the traditional way. We're going to get x is 3. So, if you're following that idea, it's the same here. The base of 5 is the same. So it has nothing to do with trying to solve this equation. All we need is this. Okay, now we could solve this. I'm going to do this quickly. I'm going to send the 2 to the other side and have the negative 2 come over here, and I'm going to get x is 2. So you could solve that in a more traditional manner. I went quickly there, but you're going to get to the same place. Okay, now here's where it gets a little more creative. If I look at this and go, well, what good is this going to do? I have 8 and 16 as these bases. They're not the same. But here's what's clever. What's clever about this is they could both be, 8 and 16 are both based on the number 2. I could create a version of 8 that is based on a number 2. Let me see how they did this here. Yeah, now watch here. So 8 could be thought of as 2 to the third. And 16 can also be thought of with a base of 2 and an exponent. It could be 2 to the fourth. Now, I hope you're following that so far. 8 and 16 really are based on the number 2. And let me show you this. If you have a power to a power, do you remember the rule? You would multiply and make this x to the 6th. Okay, so this is a power to a power, so we're going to multiply. But notice it's 3 times x plus 2. So it's going to get distributed and become 3x plus 6. And over here it's going to get distributed and become 4x plus 4. I'm following the exact same rule. Nothing has changed. I'm taking a power to a power. That's all I'm doing. Now, once I have done that, look what I have. I have the same base on both sides, and it's now, I don't need to worry about the base. I can just set the exponents together and solve. So if you look at this problem here, what we need to do, this 25 can be based on the number 5. So I'm going to turn that into 5 to the second. That's the same thing. But now I've got a power to a power. So let's do 5 to the 2x equals 5 to the 6x plus 4. Okay, I've got the same bases, so they don't matter. And all I've got to do is solve this. I'll do it in a more. I'm subtracting the 6x here, dividing both sides by negative 4. Get x is negative 1. Now, before we get too far away from this, there's going to be some on the activity that are going to look like this. Suppose I had, I'm just going to make one up now, but okay, I don't even care what it equals here, but so suppose I had something like this, or you know what, let's make it this. How could I turn this into all one base? Well, first of all, 1 over 25 is really based on 5. Do you see that I could turn it into 5 to the negative second? So how do I turn 5 into 25? I make it to the second power, but it's not on the top, it's on the bottom, so I make it a negative exponent. Now, what would I do with this? Well, we just saw in the last one a power to a power was multiplication. But suppose I had the same base and they're being multiplied, I would just add those exponents up. It would become x to the fifth. Well, even though these are very weird exponents, it's the same. I've got the same base. I would add the exponents. It'd become 5 to the 2x minus 2. Now again, there were quite a few of these on the activity, on the worksheet, and they didn't have any examples like that in here, so just wanted to show you that. Basically, all the regular rules of exponents are going to apply, no matter what form. Even though they look strange with x's, it's still the same rules. Okay, now this one may seem at first like, how do you do this? Well, it's pretty simple actually, because I can turn a square root into a fractional exponent, and I'd get 2 to the 1/2. So 5x equals 1/2. We could solve that. Well, they're being tricky here, but I'm going to divide both sides by 5. It's going to be a long process here. Keep, change, flip, but it's going to be 1/10. So the key to this is remembering that roots are fractional exponents. A square root is a 1/2 exponent. Okay, simple one here, same idea. I'm going to turn it into 5 to the 1/2 power. Now the bases are the same, so all I need is x is 1/2. Okay, now I don't know if they should have started with this one here in my opinion, but so we're going to get to a different rule here, a different idea. I cannot make these both to have the same base. There's no way. This is 3, this is 2 over here. That's not going to happen. So what I would do, our next trick, is that I could take the natural log of both sides. And what that would allow me to do, I don't want the x to be up here in the exponent. If I took the natural log of both sides, I can bring that exponent out front. That was one of our properties of exponents that was very useful, is I can bring that to the front. Now, we're going to talk about this. I'll show you where you'd go with this in just a second. But the problem is this illustration. I cannot have a natural log of -2. So again, this trick, I should back up. You could do this trick with the common log or a natural log. You could do it with any log and it would still be true. But the natural log is most commonly used for this in math. I don't know why it was settled on, but a common log would work too. So remember, a common log is just written like that, and it means log base 10. So it'd be the same thing. Okay, so we'll talk about this. This is just a number, and we could distribute it. But here's the problem. A natural log is like a log base e, and what we'd be saying is, how do I turn the number e, which is about 2.7, how do I turn that in to what exponent would turn it into -2? Well, there isn't one. There's no exponent in the world that's going to turn a positive number into a negative number, and so this does not exist. So in other words, remember, -2 is not in the domain of a logarithm. So we start this off with one that can't be done. So we're going to see the same here. I cannot get common bases out of this. 2 and -100 are not based on the same thing. There's no way I can make these both with the same base. So what I would do is try to get the exponent down in front by using that logarithm trick. The problem is, when I do that, I would be taking the log of a negative number, which cannot be done. So it does not exist. All right, now let me see if I can, I don't know if I can use theirs here, but now same thing. This one's going to work. The issue here is 5 and 4 cannot get the same base. So what I'm going to do is I'm going to take the natural log of both sides. Again, you could take regular log, it would work. I'm going to take the natural log of both sides. So like this. Now why am I doing that? Because I want to get those variables out of the exponents, and I want to get them down in front. And one of the properties of logs lets me do that. So I've got this. Now the key to this is understanding. You could crunch the natural log of 5 on your calculator and you'd have a number, and it would then follow all the regular rules of mathematics. But what happens is that natural logs make very weird, strange numbers, lots of decimal places. So mathematicians will just leave it as a number. They're just going to leave it as a log for convenience sake. Now you may not think it's convenient, but it's going to make it working it much easier. So all you have to remember is that the natural log of 5, that's a number. It's just a number, and it's going to follow all the same principles. If I had a number out that needs to be multiplied by a binomial, I would distribute it. I'd send them here and here. And that's the same thing we're going to do here. They're going to send that natural log of 5 to both of those guys. Okay, now where do we go from here? I have x's in both rooms. These are just numbers multiplied by x. That's all it is. So all the regular rules are going to apply. Well, what are those rules? Well, if I'm trying to solve an equation, I need to get all the x's back together. So I'm going to get this x to come over to this room, and then I'm going to get the 2 ln of 5 to leave. So here's what would happen. If this number changes rooms, it's going to be a negative. And if the 2 ln of 5 changes rooms, he's also going to switch signs and become a negative. So that's how I get here. Okay, x ln of 5 minus x ln of 4, they are not like terms. I cannot combine these. So what I'm going to do is I'm going to pull out a GCF. They both share this x. I'm going to pull the x out front. And then look what's left behind. I know it's very strange, but this is the GCF of x comes out. The only thing that's left is ln of 5 minus ln of 4. Now, I can get x by himself. If I had 3 times x, I would just divide the 3 away. Well, I've got x times this big long chain of natural logs. I'm just going to divide that away. Oh, they went clever on me. Hold on, let me show you what I would do here. I would just do this. That's all I would want you to do. Now, they have gone a little further than I would. You can tidy this up. You could condense this, and you would see that the ln of 5 minus the ln of 4 could be turned into... I'm not sure I care about you taking this step. At first, I just want you to learn how to solve these. So we'll do another one here in just a second, and I'll talk you through. Okay, let's try another one of these. I cannot get these down to the same base. There's no way. So what I'm going to do is I'm going to take the natural log of both sides. Okay, now I've taken the natural log. It allows me to bring those exponents out to the front. Now, why is that useful? I can now solve this by all the regular rules if I just treat this like it's a number. So here's what I'm going to get. I've just distributed this. That's all I've done. I've sent him there, and I've sent him there. Now, I'm going to get all the x's back together in one room. So I'm going to do this. Do you see what I've done? I've just moved that over by subtracting them to the other side. Now, I did that trick. I've got 2 x's that can't be combined. What can I do? I'm going to pull out a GCF of an x. Now this here, all of this in parentheses, that's a number. I'm going to divide both sides by the ln of 2 minus the ln of 3. As strange as it looks, it's just a number. And I get x equals the natural log of 3 of the natural log of 2 minus the natural log of 3. I know that looks very strange, but you could crunch this and you're going to get a value of x. It's going to be a very strange number with lots of decimals, but mathematicians will just leave it and work with those natural logs. And there we go. Now I know it'll take some getting used to, but you'll actually see it's not too bad. Okay, now I've got one more basic idea here. I think maybe I've got a couple. Give me just 1 second here. I need to pause the video. All right, this is an entirely different trick here. What we want to do is, if I ever have an equation that has a difficult portion, something like this, What I'm going to do here is I'm going to try to isolate that difficult portion. So this should have been an equation here, whatever. I'm going to isolate the square root or the x squared to try to get that all by itself. Well, that's the same trick I'm going to do here. E to the 2t is a strange problem. I need to isolate that, and the way I would is I'm going to treat it as if it was just a giant I don't know. If all of that was I don't know, I would just divide both sides by 20 to get it alone. Well, I'm going to do the same thing here. Now I've written over top of it, but if I divided both sides by 20, I would have 5 equals e to the 2t. Okay, well I've now isolated the difficult portion. Suppose I had square root of x equals 5. What I would do next is I would then square both sides to do the opposite of a square root. I can get rid of a square root by squaring it. Well, how do I get rid of an e? I would do it by taking the natural log of both sides. So the opposite of an e is a natural log. Those are opposites and will knock each other out, just like squaring both sides are opposites and would knock each other out. It would do the same here. Now there's a little more to the story here, but if you do it to one side, you got to do it to the other. But essentially what happens is because the e and the natural log are opposites, you're going to wind up with just 2t on this other side. Now, we're going to continue just treating natural log as if it's a number. We're going to divide both sides by 2 to get t alone. I've got the natural log of 5 over 2 equals t. Okay, so let's try it again. We're going to get the problem portion alone, which is e to the 0.5t. That's what we want to get alone. So we're going to do it by dividing both sides by 3. Okay, so now I have the problem alone. Let's do the opposite of e. Well, the opposite of e is a natural log. If you do it to one side, you've got to do it to the other. These are opposites, so all I'm going to have left is 0.5t. Over here, I'm going to have the natural log of L over 3. So that's all of one number. Now to get t alone, I'm going to divide both sides by 0.5. And so t is going to be the natural log of 11 thirds divided by 0.5. Okay, let's try another one here. We have a little more complicated story, but we're going to get e to the 2x by itself. I'm going to subtract 5 from both sides, and then I divide by 4. I'm going to treat it just as if it was 4x plus 5 equals 12, at least to start it, to isolate the problem portion. So subtracting 5 from both sides, divide both sides by e. Now I've got this alone. Well, let's now do the opposite of an e, which is a natural log, which allows me to just have 2x on the left. But if I do something to the right, I got to do it to the left. I got to do it to the right as well. Got one final step. I divide both sides by 2. I don't know if they're going to. Yeah, there's another clever trick they could have done, but let's try another. We're going to get e to the 2t. This one's okay. I didn't expect this trick. E to the 2t and 7e to the 2t. This works like a variable. This is the same as if I had 1x and a 7x on the other side. Because this is exactly the same type of e, it works as if it's a variable, and they're the same kind. So before we do our trick, what I'm going to do is I can just get these back together. I'm going to subtract e to the 2t here. If I do it on one side, I've got to do it to the other. Because they're the same, I knew I could actually put these together. And I'm going to have 3 equals 6e to the 2t. Does that make sense? So it's like I have one of them I've taken away, just as if I had 7 and if I subtracted, it's all the same rules. If I took away an x on both sides, I'd have 6x. Well, I've got 6e to the 2t's. Okay, now let's divide this. I want to get this e to the 2t all alone by dividing both sides by 6. Now, I'm down to e. I've got the problem portion isolated. I'm going to take the natural log of both sides, and I'm going to get this. If I take those opposites here, I'm going to be able to knock that out. Okay, I was expecting some more here, but it looks like we're done. This is what's going to happen in the next section as well. We're going to continue this idea. It's a little challenging. It's going to take a little more thinking, but hopefully you see some basic patterns in this section that we can use. We'll learn a few more in the next.